Thank you very much. It's great to be here. I'm going to put a little disclaimer here. If you've taken a reinforcement learning class, you might have already seen a good part of this talk. But I tried to make it self-contained, and I tried to add a little bit of newer stuff for people who have seen off-policy learning before. So hopefully everybody gets a little bit out of this. I have to thank Rich Sutton because a lot of these ideas and a lot of the actual slides came from him as well. So we're going to talk about off-policy learning methods. The idea is to learn the value of a target policy from experience that's due to a different behavior policy. So why is this interesting? Well, for example, we may want to do control, so we may want to figure out what's the best policy. We don't know it ahead of time, and so therefore we can't actually generate experience with this policy. And so maybe our behavior is something like epsilon soft, some kind of exploratory policy, but we are interested in an optimal target. Or you might actually work on a practical application of reinforcement learning with, let's say, a healthcare provider or a commercial entity who might be able to generate data for you in the form of trajectories, but they will not typically let you run your own policy in order to generate data. Rather, they may have some behavior that they use as common practice, right? So for example, if we're working with a healthcare provider and they're trying to figure out how to do optimal treatment design, they may do randomized control trials in which the data is generated with a particular behavior policy, but you're again interested maybe to figure out the value of an alternative way of doing things instead of an alternative policy. So from a practical point of view, this is a very important problem. My own interest in off-policy learning has actually come from neither of these two things, interestingly, but actually from the desire to sort of do reinforcement learning for what people would think of as real AI, so a system that may be able to use one stream of experience in order to learn about many things and to kind of understand how the world works in some sense. And so in that case, doing off-policy learning is necessary because we may want to take one stream of experience, for example, one stream of data generated by a robot going around, and try to learn about many different other behaviors at many different time scales and with respect to many different measurements. Okay, and so in that case, the goal of off-policy learning really is to kind of multiply the learning that you can do from one stream of experience. So for all of these reasons, off-policy methods are quite interesting. They've been around for a while. Typically, we will make a restriction that says that the behavior policy has to have coverage over all of the actions that the target policy may take. That's quite reasonable because if we don't see an action, there's no way to learn about it. And a lot of the methods revolve around an idea from classical stats called importance sampling. Which is that we want to take the data that we get, and because it's not really coming from the right distribution, we want to reweigh it appropriately. So we're just going to do a quick review of importance sampling in general, and then we're going to look at how exactly it gets applied in reinforcement learning. So importance sampling, it's typically something that's talked about when you're trying to estimate an expectation of some function f with respect to some probability distribution p. And so think of p as the target distribution. And so, how do you do this from samples? Well, you might query samples from P. If you're lucky, you're doing supervised learning, you can get IID samples. You can take the values of the function f at these samples. You can average them. Okay, so if you have big N samples, we can compute an average. And we know by central limit theorem that this is going to converge. This is a consistent estimator. It's unbiased, and so on. Now, the tricky thing is we may actually not have access to P. Okay, instead, we might get our samples from some other distribution Q, which I'm going to call proposal or sampling distribution. And we still want to do this kind of estimation with respect to P. Okay? And so that's the setup. And you can do this very easily with a very simple trick, okay, which is called the importance sampling trick. This is its usual form, if you will, where if we're trying to do the expectation of F over P, we might just multiply and divide by Q, okay? And so now we have an expectation with respect to distribution Q over here, okay? And that expectation is of F multiplied by P on Q, all right? So we just reweigh the samples that we're getting according to how likely they are under distribution P and under distribution Q. if a sample is very important for P, but is not so important for Q, then it might be very highly weighted. Samples that are coming from Q, the run-of-the-mill from Q, may be downgraded, okay? And other than that, we can still do now our estimation by taking the values of these reweighted samples and averaging them together. And so the main requirement here is that we want this fraction to be well defined. So if P is non-zero, Q also has to be non-zero. This is this idea that you need to have support wherever you want to do the estimation. Okay, now there's a slightly sort of better estimate here, okay, that we can get. One of the problems with this estimator, of course, is that if P and Q are very different, okay, then these weights here, or these ratios, might actually be very big or very small. And so this estimator that we have here may have high variance. And so there is a different version of this called normalized or weighted importance sampling, which actually uses these P on Q ratios as weights and does a weighted sum, okay, instead of a normal averaging. And so over here, in this estimation, instead of dividing by n the number of samples, we would divide by the sum of these weights, okay, by the sum of the P on Q. And that leads to an estimator that has typically lower variance, but is actually biased, okay? So if you have very few samples, it'll be biased towards the sampling distribution or the proposal distribution. But the bias washes off in the limit, so in the limit it's a consistent estimator. So this is where very well-known stuff. It was developed in stats. It's applied in simulation quite a lot, and actually the simulation community has developed other versions of these ideas in order to reduce the variance. But now we're going to try and take a look at how do we apply these general ideas to reinforcement learning, okay? And so in reinforcement learning, we're interested in these quantities called value functions. A value function is an expectation of the return. And so the function of interest for us is going to be the return. That's our function f. And now we're going to have a target distribution, which is the distribution of trajectories under policy pi. We're going to have a proposal distribution, which is the distribution of trajectories under the behavior policy, which I sometimes call B, sometimes I call mu. I hope you don't get too confused about that. Of course, the problem here is that if we're thinking of the probability distribution over the space of trajectories, okay, trajectories can be very long, and these distributions actually can get very, very different from each other. So pretty much the rest of my talk, or maybe 2/3 of the rest of my talk, will be dedicated to try and exploit some kind of structure in P and Q that would help us reduce this variance, okay? And because we're in a reinforcement learning setting and we're talking about trajectories and we might live in a Markov decision process, there is some structure to P and Q that we hope to be able to exploit. Okay. And so this is going to be the topic of the next couple of slides. Okay. So first of all, what is the probability of a trajectory? Okay, we're sort of spelling this out over here. The probability of a trajectory is given by two components, okay? One is how likely are the different actions that are happening on this trajectory, okay? So pi ak given sk is the probability distribution of an action at time step k given the state that the agent's in. And then we have the environment that plays a role, so these p sk plus 1 given sk ak, this is just the dynamics of the environment, okay? Now, if you're a reinforcement learning person and you see a distribution that consists of these products, you could be a little bit worried now because we actually don't know the environment, okay? And so the dynamics of the environment is unknown, so therefore we cannot actually compute this probability distribution. But luckily, we're going to get some simplifications because we are in a Markov decision process. And so the way that this is going to work is we're going to consider what's the probability of a particular trajectory under the target policy pi and under the behavior policy b, okay? And the importance sampling ratio says we're going to take these two probabilities and divide them together, okay? So we're going to take the probability of the target distribution, the probability under the behavior distribution, divide them, and because it's the same environment, okay, and because we have this nice structure, Markovian at every step, these dynamics of the environment are actually going to cancel out, okay? And so if I want to compute the probability of a trajectory under the target and the behavior policy, I'm actually going to end up with just a product here that has the target and the behavior and nothing else in it. All right? Now, these are quantities that presumably we will get a handle on, right? Because the behavior is something that the agent is using, all right? And the target is the thing that the agent's interested in. I am going to discuss a little bit what happens when we actually don't know the behavior. That could be the case, for example, if we're working with data that somebody else is generating for us, okay? We can handle that a little bit as well. So this ratio over here, okay, is the quantity of interest. This is what we're going to use in the vanilla form of this algorithm in order to control for the off-policyness of the data, okay? And this is sometimes called the importance sampling ratio, but as you can see, it also has this kind of structure that it's made as a product of per step importance sampling ratios. And notice also that all of these importance sampling ratios actually have expected value 1. Okay, why is that? Well, the data is actually made by the behavior policy B. So if I want to compute the expected value of rho, the probabilities of these trajectories would be just what's in the bottom under B. Okay, and so we can simplify and we will get proper distributions that sum to 1. Okay. Are there any questions or comments so far? Are we good with? This is sort of the very basic idea, and all of the coming algorithms are going to rely in some way or other on this idea that we can compute these importance sampling ratios and use them to reweight returns. Okay. Okay. So now we're going to start looking at some algorithms. Okay. And so here we have some trajectories. Okay, this is trajectory data. We have an agent that's going over time steps. There's some states at which we start these trajectories. Maybe we're trying to estimate the value of state S, and we see the value of state S at time step 4, and again at time step 20. And imagine that in this case, we're simply doing Monte Carlo estimation. Okay? And so we want to compute the expected value of the return. We're going to let the system run until the end of the episode. We would average normally the returns. But here, because this trajectory is generated by the behavior, we can't just average simply. We need to reweigh, okay, by the probability of these trajectories. So for example, for the state 20, we need to reweigh the return that it gets by the ratio, the importance sampling ratio of the trajectory from time step 20 onwards, okay? And for the occurrence here, we need to reweigh but the trajectory from time step 4 onwards. Okay? And so our importance sampling estimate for the value of state S is this average of the returns weighed by the importance sampling ratios over the entire trajectory. Okay? And here we're simply going to do averaging. So we're using the regular form of the estimator, and we're dividing by the number of trajectories that contain state S. Okay? So this is assuming everything is tabular, right? Every state has its own entry, and so on and so forth. It's sort of the simplest importance sampling algorithm that you can imagine. Yeah?
So the rewards are only state dependent but not on state and action dependent, is it?
So in this particular case, because we're doing policy evaluation, we don't really care about the actions. But of course, you could do the same kind of thing with state action pairs. So if you wanted to evaluate a Q value instead of a V value, you could just condition on the state and action and then do the same kind of process, but for state action pairs. Okay. Any other questions? Okay. Now, what does weighted, oh, sorry, yes. The rows are known. Now, why are the rows known? Because because actually the rows don't have P in them at all. The P has simplified. So the rows are simply a product of these ratios of pi on B, okay? And pi is something that we know. It's the policy, it's our target policy, it's the policy we're trying to evaluate. And B we also know in this case, it's the policy that's generating the behavior. So for example, B might be something like uniformly random. Pi might be, let's say, the policy that always picks a certain action, right? Just to give an example, I know these ratios at every time step, therefore I can compute this product over the entire trajectory and everything is fine. And this again relies crucially on the assumption that we are in a Markov decision process, and so therefore the structure of these products can be decomposed into the dynamics of the environment and the dynamics that are under the agent's control, and the environment cancels out. Okay. Any other questions? Okay. Okay. So now we can do ordinary importance sampling. We can also do weighted importance sampling. Okay. What does weighted importance sampling do? Well, instead of dividing here by the number of trajectories that contain the state S, okay, the number of times that S occurs in our data set, actually divides by the sum of these importance sampling ratios. Okay? So in other words, like if you glance at this formula, it really looks like we're taking the returns, and instead of averaging, we're doing a weighted average, okay, with the same weights on top and on the bottom. All right? So now let's think a little bit what happens if we have a single trajectory in our data set. Okay, so if we have a single trajectory in our data set, there's going to be one return. Okay, it will be weighted by some row, but that row will appear on top and on bottom, and it'll actually cancel out. Okay, and so really our estimate is going to be just the return, which is clearly wrong. Okay, because the return is generated by the behavior policy. So this is the sense in which this kind of estimator is biased. Okay, when we have a small sample of data, this estimator is not giving us the value of pi, it's giving us the value of B. Okay, but as we're going to see next, okay, the advantage of doing something like this is to reduce variance, and the variance can be a huge issue. Okay, and so this is a picture here showing Monte Carlo, okay, Monte Carlo estimation with ordinary importance sampling, and these are just independent runs of this algorithm, okay, through a data set. This is number of episodes, and we have a very small task over here, this tiny MDP, okay. And what you can see is that we get, first of all, very big instabilities, okay, and also we can in fact get divergence. Okay. Now, why is this happening? Well, we have trajectories here, and the trajectories are using these products of ratios. Okay, and so the variance that happens over these products of ratios is very high. And furthermore, if we let these episodes go to infinity, the variance actually can go to infinity. Okay. Now, there are sort of ham-fisted ways of reducing the variance. For example, we can just say, oh, we'll cut off episodes after some number of time steps. Okay. I will not let any episodes longer than 5 time steps or 10 time steps go by. That's okay, but it's sort of not an elegant solution. Okay. A more elegant solution is to actually use the weighted importance sampling estimator, which has a little bit better behaved variance. And let me just show you an example of this. Okay, so this is weighted importance sampling combined to ordinary importance, sort of compared to ordinary importance sampling in a particular task, which is blackjack. And here you see that the weighted importance sampling estimator is actually much, much better. Okay. Now, theoretically, the variance of the two is actually not comparable. Okay. But in practice, the weighted one tends to be better. The disadvantage of the weighted one, as I've presented it before, is that it needs a weight over the entire trajectory. Okay? There has been some progress made in making it an incremental algorithm. Rupam, who's going to talk in a couple of days, has done some of that work, so you can ask him about that if you want, how to compute the weighted importance sampling estimator incrementally. It can be done in certain cases, but in general, you may need to wait until the end of the episode. Okay, so Now we're going to talk a little bit about other ways of reducing the variance which do not rely on weighting, okay? And all of the stuff that I'm going to show you is essentially trying to further exploit the fact that we are in a Markov decision process, and therefore we can do things per time step rather than per trajectory, okay? So the first thing that we may want to think about is that, in fact, these trajectories also have a gamma, okay, the discount factor. And the discount factor is in some sense introducing a time horizon. Okay? So for example, if gamma is equal to 0, I'm only interested in one time step. I'm only interested in what happens immediately and nothing that happens afterwards. So taking a weighting on an entire trajectory does not really make sense, because all we're interested in is in the first time step, and so we could get by just waiting on the first time step and sort of ignoring everything that happens afterwards. Okay? And certainly that would have smaller variance. And so the discounting aware importance sampling essentially plays around with this idea. It basically says, if you imagine that you have some partial returns of a particular length, okay, so here's a return that goes from time step t to time step h, okay. The discounting is telling us what's the likelihood of seeing this particular trajectory, okay. And this likelihood is now not coming from the behavior, but actually from whether you terminate or not when the environment tells you, right? So if you think of gamma here, the discount factor, as a probability of your trajectory continuing at every time step, okay, then the probability of seeing any trajectory that goes from t to h is gamma to h minus t minus 1, okay? That means the agent lived on the first time step and the second time step and so on up until the end of this little snippet of trajectory. And so we can take the return, we can write it out as a sum of these truncated returns. And when we do now importance sampling, for each of these truncated returns, we only need to think about the correction over this truncated trajectory. So rather than considering everything until the end of the episode, we can just consider a ratio here that goes from t to h minus 1. Okay? And we can do this with normal importance sampling. We can do this with weighted importance sampling. Questions? Yeah? So an episode means the agent starts at the beginning and goes until a terminal state is reached, okay? And a run means I start the learning from scratch, and now I do a whole sequence of episodes, and the agent keeps updating its value, okay? And so typically we will do multiple runs for reinforcement learning agents because, as you could see in the picture, the behavior can actually be very different for the same algorithm on different runs, right? Just because of coin flips, essentially. And so typically when we plot, either we plot all runs or we plot some kind of summaries with error bars around these averages. Yep. So we are weighing all of the samples equally, okay? But what is true is that as a sample gets longer, the likelihood, right, this row actually goes to 0, right? Because the longer a trajectory is, the more unlikely you are to happen on something that the target policy would really do. And so this is one of the problems with these algorithms is as your trajectories get very long, you may get these ratios that are close to 0 on many trajectories, and just on some trajectories you will get some useful data. And we're going to see in a minute another solution that's actually a little bit better at fixing that problem. Yeah?
So are we now in tabular setting?
Right now we are still in tabular setting, although these ideas that I'm explaining to you would apply just as well in the function approximation setting. We'll discuss that in a minute also. Okay? Other questions? Okay. Okay, and this is just to sort of give you a hint that these are orthogonal ideas. This is a weighted discounting aware importance sampling, Okay? And again, the idea here is that instead of dividing by the number of times the state S appears, we're going to divide by the sum of the ratios, okay, the correction ratios. And these correction ratios always have a component that tells you how likely you are basically to last this whole trajectory, and then a component that tells you about the likelihood of the snippet of trajectory under the two different policies, okay? And these two things, you know, the fact that we have a product here basically tells you these two are independent events, right? We're going to, so this kind of formulation is actually useful in the case where you're thinking about temporal abstraction or options or things like this. You're going to talk about this later on in the week, so just keep that in the very back of your head. Okay. Now, there's another interesting thing that we could consider, okay, which is that the return itself has some structure, okay? So far we treated the return as a block, right? It's the function whose expectation we want to estimate, but we know that in reinforcement learning, we can actually break up the return into a reward part and the next time step, and so on. And because of Markovian property, this nice structure allows us to kind of partition things, okay? And so in particular, okay, imagine that you have an episode, okay, and this episode starts on time step t. And so the return on this episode is gt, and rho t here is the importance sampling ratio from time step little t to the end of the trajectory, which is signaled by big T. So now, what is this return? Well, this return is the sum of the rewards that we get at every time step. We waited until the end of the episode and we computed rho t, okay, at the end of the episode, the correction. But actually, it also has an interesting internal structure because it has all of these products that are coming from every time step. Okay? And in particular, if I focus on a particular time step here, t plus k, all right, the reward at time step t plus k is due to the actions that the agent took before time step t plus k, all right? But what happens after time step t plus k really does not matter, right? Because the agent will continue its life, take some decisions, and if I think of what's the expected value of all these ratios that are coming afterwards, this is actually all 1, okay? So really, I don't need to use a whole product for the whole trajectory in order to weigh the reward at time step t plus k. I could just use the product from the beginning of the trajectory, t, okay, all the way to t plus k, and everything that happens afterwards does not really matter. Okay? So this is pretty much similar idea to the discounting aware importance sampling, except instead of thinking what's the likelihood of this trajectory happening because the agent is still alive, we think what's the likelihood of the trajectory up to this time step happening because of the policies that are being involved. And so now we can sort of develop this a little bit farther, okay? And essentially rewrite the expectation, okay, the expectation of a reward here, as the expectation weighted by just this sort of partial importance sampling factor, okay? And this is an equivalence that we've shown back in 2000 to be exact. And so instead of using a return that's weighted by a big fat product importance sampling ratio, we can actually use an estimator that takes rewards and weighs each of them by the product of importance sampling ratios that is appropriate, okay? And so, you know, in principle, these snippets can have smaller variance, okay? Also, as was pointed out before, it's less likely that these things go to 0 quite so fast, right? So at least some of these snippets you would expect to contain some information and not to be completely washed out, okay, by the algorithm. So now this is going to be our algorithm here. It's sort of what we call per reward or per time step importance sampling. That means that we don't use the real return. We actually use this return that is incrementally computed And if you've seen Adam's talk this morning, he probably talked about temporal difference learning, you can kind of see that this is a formula that you can easily take and implement in a temporal difference learning style. Okay? Yes?
So if the Markov property tells us that the value of the state doesn't depend on the previous states that were observed, why does the reward at time t plus k need to be multiplied by an importance sampling ratio that's affected by previous states?
Yes, that's a great question. Let me show you this picture, which kind of explains that, okay? So let's sort of think of this from the perspective of how does information propagate, okay? So I started my trajectory here, all right? There are some choices of action that are happening. These choices of action are happening based on the behavior policy, which in this case is denoted mu. But really we're interested in this other policy, which is pi, all right? Now what we're asking is, okay, I've arrived at some point in the trajectory, xt, okay? At this point I've observed an outcome, right? And I've also observed an error. So delta t here, think of this as a TD error that I'm getting at time step t. What I would like to know is how to assign the credit for delta t all the way to the beginning of the trajectory. Okay? In other words, how should this error flow back in time to the previous states? Okay? And so the reward at time step t, right, is the one that is generating this delta t, reward plus the value function. And so when we're doing this kind of assignment, what we're really saying is I want to take only so much portion of this error as would correspond to this trajectory under pi. Okay? And so I need to weigh this delta t by the likelihood of this trajectory that is happening under mu versus under pi. Okay? So it's not like the values are still Markovian, the values still depend only on the state. The reward, the immediate reward only depends on the state. But when we're thinking of doing this kind of long-term credit assignment, we need to take into account how likely it would have been to see this error. Okay? Now, in an extreme case, let's say that we're trying to estimate something like the value of the greedy policy, okay? But on this trajectory, at some point we took a random action, all right? That action may have zero likelihood under the target policy, all right? So what will happen is that this delta t won't flow all the way to the beginning, okay? It will only flow up to an intermediate state where things were still on policy, and then the flow will be cut, okay? And so the rationale behind it, the intuition behind it is if I have an agent that knows how to perfectly play, let's say, Go, it's been playing a wonderful game, it did some exploratory move in the middle, it ended up losing, I don't want that loss to get propagated all the way back to the beginning of the trajectory and destroy my beautiful policy. I only want that to be associated up to the point where this sort of silly action happened, and that action will get punished, but at least I won't sort of propagate the blame too much. Okay? So by the way, this kind of thinking is part of a larger sort of problem in reinforcement learning called credit assignment, right? How do we do credit assignment efficiently for things that happen later on to things that happen earlier on? And that's a big open question in some sense, and we have a lot of good answers, but in the off-policy case, that's part of the big problem. Okay? Any other questions? Okay. Let me see. I don't think I wanted to say anything else here. Okay. Okay, so now let's think a little bit about how we are going to actually implement this kind of algorithm. Okay, and so if I think about this from the perspective of something like updating action value functions, I have a TD error here, delta t. Okay, and so you compute this just like you normally would a TD error or a Q-learning error or a Sarsa error and so on. Okay. But now we also want to sort of use this importance sampling ratio product, okay? And has Adam talked about eligibility traces, by the way? A little bit? Okay. So basically, the eligibility trace is this computational gadget that tells you how much credit or blame you want to assign to things that have happened previously in the trajectory, okay? And so one way we can think about implementing this kind of product is actually through an eligibility trace mechanism, okay? And so at every time step in the trajectory, for the state X and action A, I have an eligibility that says how much do I want to update this based on the error that is happening at later time steps. And so its eligibility is basically sort of accumulating these factors, all right? And whenever I want to make an update, I'm going to make an update to it, but I'm going to weigh that update by this kind of factor, okay? And in this case, we have a gamma t, which is sort of the horizon, right? Is the agent still alive? And we have this product of the importance sampling ratios. So actually, this is very easy to implement incrementally and online. At every time step, we compute delta t, we update the eligibility trace by multiplying it by yet another factor of pi on b, and then we do an update, okay? So that's kind of cool, okay? As you might imagine, we still have a problem with these ratios possibly having very high variance, or if we go on for a very long time, going towards 0 and so on. And so now we're going to talk about some further solutions to solve that problem, okay? And the first solution I'll tell you about is called recognizers. This is something that we did back around the mid-2000s. And in some sense, you can sort of interpret this as giving up, okay? In the sense that if the behavior and the target policy are very, very different, okay, then the ratios are going to just have very high variance, and there's not much that you can do, okay? And so the idea of recognizers was actually to not be so ambitious as to take an arbitrary behavior and an arbitrary target and try to glom them together, but actually to make a target policy that is somehow aligned with the behavior policy, okay? And so one way you can do this is by taking the behavior policy and multiplying it with something that you can think of as a recognizer, okay? That's something that recognizes if this action is interesting or relevant in the state or not, okay? So in this case, rho is given, okay? Rho is given, the behavior is given, and we make up a target policy that's basically modulating on top of the behavior, okay? So this is the picture over here. For example, we might have a behavior policy that's continuous and sinusoidal like this, and then we might say, oh, I only want to recognize actions that are within a certain interval, okay? And so I can put a recognizer here that lights up when the action is within this interval. Then I take this and I renormalize and I obtain a target policy, okay? And so this blue curve here, this sort of faded blue curve, is the target policy obtained with a recognizer, okay? So you can see that it's actually not arbitrary, right? It's really derived from the behavior, and then this area is pretty aligned with the behavior. It's not identical either. And if we actually try to do now importance sampling with this kind of policy with a recognizer, we can actually do this really well, okay? So here we're looking at doing importance sampling with the recognizer, okay? And you can see that the variance is actually really low and we converge very quickly, okay? Okay, now the question is, how do I recognize that something is interesting or important? Okay? And one possible source is by seeing demonstrations or human data. So for example, if somebody is performing some actions and we think that this person is pretty good at the task, then maybe those actions are interesting and the areas around those actions are interesting. And so we could define a recognizer essentially by supervised learning by using human data. But in general, the problem of where these things come from is currently open. What we do know about this, this kind of recognizer is that it actually minimizes the one-step importance sampling variance, okay? And of course, if you recognize more actions, it's going to lead to lower variance because you're becoming more and more on policy. And it folds into the eligibility trace basically just the same as an importance sampling correction. The other interesting aspect of this is that we actually don't need to know the behavior policy. And sort of to see this, right, if you look at this target policy over here, right, pi is made up of b times rho, Okay, so if I divide pi by b, b cancels out. I have the recognizer, and then I have like a little normalization constant in the bottom, but that's something that I can just estimate empirically, right? If I come back to a state, I can just see, right, what things are being done and estimate this empirically. And so in fact, I could use this technique even if I don't know what is the behavior policy, which again may be the case in certain applications. Okay, any questions? Yeah.
Here, when we are making the assumption that rewards scale linearly with the ratio of probabilities of action.
No, we are not making any assumptions about the rewards because this is all having to do with the corrections, right?
I mean, the previous slide, when we are writing the reward function, we are multiplying each reward function with the ratio, right?
So we are not making assumptions about the rewards really, because the rewards are whatever comes from the environment. All that we're assuming is that we have a sequence of interactions with the environment that obeys the Markov property. That's all. But we're really not making any assumption about the rewards. The rewards are whatever comes from the environment. We reweigh them according to our probabilities, and that's it. Okay? Yes?
This might be a slight tangent, but why does Q-learning not have some correction term?
So Q-learning does have a correction term, and I will show you that in a minute. Okay? Other questions? Okay. Let me just sort of skip ahead. That's okay. That's my life right there. Okay. Okay. So let's think of some other ways that we could do this, okay, that are sort of more Q-learning-like, okay, and less important sampling-like, okay. And so I'll show you another idea. This is called tree backup. This is actually, at the time that we came up with the important sampling work, this was really my favorite algorithm. Yeah. So I'll tell you a little bit about it, and then I'll tell you what problems it has, and we'll fix that too. So this particular algorithm basically says, imagine you're going along the trajectory, okay? You arrive at a point, mu, the behavior, is taking some action, but pi would take some other action. So actually, there's like a little tree here of all the kinds of things that pi would do, okay? How do we want to correct this, okay? And so the inspiration actually comes exactly from Q-learning, all right? Q-learning would basically say, I'm going to, whatever mu is doing, I'm going to actually back up with the max, right? I'm going to imagine that pi is acting and is doing the best possible thing, and we're going to back up with the max, all right? So what it does, right, one way to think about it is it will reweigh the trajectory, right, according to the target distribution. The target distribution in that case is deterministic, it's ones or zeros. And so whenever you actually go forward with a greedy action, you will sort of continue to propagate information back, and otherwise you won't. So this is an algorithm that uses eligibility traces and Q-learning. It's called Watkins Q-lambda. And in this case, we're going to do something very similar, okay? But we're going to do it by using pi, right? Which is our policy, which is just a sort of a strict generalization. So pi may be anything between 0 and 1, but essentially we're going to take whatever errors are coming and put a weight on this trajectory. It's just the product of the pi's. And in the tabular case, this actually also computes exactly the right answer, okay, and has sort of Watkins Q-lambda as a special case. There's one problem with this kind of approach, which is that, you know, we're multiplying now pi's here. And so as the trajectory gets longer and longer, actually this definitely goes down towards 0, right? Because we're going to kind of go all the way down. So it doesn't propagate information that efficiently further back in time. But if I'm at a particular state and I'm going forward, it's pretty good. And the variance is definitely better because here, instead of these ratios that can be very big or very small, we just have things that are bounded between 0 and 1, right? Okay, so that's the basic idea, and again, it's very similar to Q-learning. This is probably something that you've seen this morning with Adam, which is doing these kinds of backups that consider at a particular state action pair all of the possible next state action pairs. And so Q-learning here would do a max, whereas the algorithm that I just showed you, tree backup, would do an expectation here over the possible next states. And then wherever we end up, whatever action we end up taking, we would continue with that. Okay. Okay. There's incidentally another algorithm, which I'm not sure if Adam showed you or not, called expected Sarsa, that is very similar as well. Okay. And it's kind of a weird hybrid between on-policy and off-policy learning. So expected Sarsa basically says we're going to sort of assume that we are on policy. Okay, so whenever we take actions, we're going to sample the actions according to our current interesting policy. But when we're doing targets here, we're going to do an expectation at the target. Okay, and so at the target, we're basically averaging the action values according to the policy pi. And so expected Sarsa is a little bit like Q-learning in that it's sort of considering all of the possible actions, but instead of doing a max, it's doing an averaging. And so you can imagine, for example, now having an epsilon greedy policy. If that epsilon is going to 0, this is becoming more and more like Q-learning, right? But in general, it might stay average. And incidentally, if we look at sort of particular examples that are like this cliff walking task, expected Sarsa is actually quite a good algorithm, works better than either Q-learning or Sarsa, and ends up with nice performance in the end. Okay. So now I just want to sort of discuss a little bit what happens with Q-learning when we have eligibility traces, and how can we get actually algorithms that work well with these kinds of ideas. Okay, so again, further trying to reduce the variance by whatever means possible. So Q-learning with eligibility traces is this Q lambda algorithm that basically says, no matter what happens, we're going to decay errors at a fixed rate. Okay? That fixed rate is controlled by a parameter lambda. And for a long time, people have sort of been mystified as to whether this algorithm converges or not. It turns out, based on this paper by Anna Haratunian and colleagues, that this algorithm actually, in fact, does converge. Okay? But only if the behavior and the target are reasonably close. Okay? And in that case, the crux of this argument is the usual kind of reinforcement learning argument, which is a contraction argument. Okay? And so you can show that if these two policies are close enough, you can do these kinds of updates, and you will converge. Okay? Obviously, you won't converge to the correct value for the target policy, but you'll converge to something. If the two are very different, then there's no convergence. And so now we're going to look at sort of a menu of algorithms and try to reason about how to get convergence and also how to get these algorithms to behave well. Okay? And so for this, we're going to look at sort of a general blueprint of an off-policy learning algorithm. Okay? And this is a general case that encompasses a lot of the ones that we talk about today, including all the ones that I mentioned so far. So what does this algorithm have? It always wants to know how to compute an update to Q at a particular state action pair that has happened earlier in the trajectory based on a target, okay? And this target is always the reward plus some version of the expected value of the next state, right? So this is a TD error kind of term. Now this expectation here might be computed exactly by averaging, right? For example, by averaging with respect to pi, or it might be computed by sampling, okay? By taking a sample. And so in the vanilla algorithm that I presented first, we were just taking samples, okay? And you can think of it as using this expectation just based on samples, whereas something like expected Sarsa tree backup would use an actual expectation here. So that's one dimension along which these algorithms vary. The other dimension along which they vary is how do we actually compute these corrections? Okay? So the correction is always a product of factors. these factors are coming from the trajectory between when XA has happened and when this error is happening, okay? It's always going to be a product here because of the Markov property which holds, but exactly what the factors are is different, okay? And so in vanilla Q lambda, the factor is just lambda, it's fixed, okay? If we're doing proper importance sampling, this factor is pi over mu, so it's the usual kind of correction thing. If we're doing something like tree backup, this factor is actually a lambda times pi. And this is nice, but it's actually not really efficient because even if you're on policy, this is going to decay the traces much more aggressively than perhaps you would want. And so there was a solution that was proposed again by Munoz and colleagues, which is to use what they called retrace lambda. Okay, so retrace lambda is an algorithm that actually sort of thresholds the importance sampling ratios. Okay? And so what does it say? It says, I don't want ratios that are too big because that is causing instability. Okay? And so we're going to threshold these importance sampling ratios, upper bound them by 1. Okay? And so the variance is going to be lower sort of by default because we're limiting the range of these factors, therefore we're going to limit the range of the product. Okay, it still cuts the traces when it's needed, so it's going to be convergent, okay, but it's going to be slightly more efficient when it's on policy than tree backup is. And they did a nice sort of theoretical analysis of this algorithm in the case of control, actually, and so they show in their paper that under certain assumptions, this algorithm actually converges to Q star, okay, which is the optimal action value function. This is all in the tabular case, okay? But still, it was a very exciting result because the convergence of this eligibility trace algorithm with Q-learning, even in the tabular case, had not been established. It was an open problem since '89, and so they solved it just a couple of years ago. And the main concern that they have is that the target policies, okay, the main assumption is that these target policies, pi, have to become increasingly greedy. Okay, and there's a sort of a technical way to phrase that, but you might imagine that this is necessary because if I want to converge to Q star, I want the backups ultimately to be according to a target policy that is good. So that's totally understandable. Interestingly, they actually don't require the behavior policy to be greedy, and so that's a very nice feature of this algorithm because the behavior policy, if you're handed data, might be arbitrary. Okay, and so you don't need to sort of work hard to generate data in a particular way. And so this algorithm works theoretically in the tabular case. It does not work in the function approximation case. I'll talk about that in a minute. Okay, but it does work quite well in practice with function approximation. So I just wanted to show you some results. So this is taken from their paper. This is Retrace working in Atari games. Okay. And this is a comparison with these blue curves are all DQ1, which is the sort of state-of-art implementation of Q-learning using deep networks. I think Anna and Matteo will say a lot more about that on Thursday. And these red curves over here are the retrace algorithm working on top of DQ1 in several games, and you can see that this is overall quite good performance. They also did some explicit comparisons of retrace with tree backup. Okay, and so this is essentially a sort of a normalized score that tells you how much better comparatively algorithms are for if they were to be played against each other in some sense. And so what you can see is that retrace dominates both tree backup, and they both actually dominate Q-learning a lot. Okay. So these are algorithms that actually in practice can work quite well. Questions or comments about retrace?
So for the correction term for Q-learning was lambda. Doesn't it assume actually that we know the optimal Q, because only in that case is that the difference between these two policies becomes lambda?
So what we do is we basically assume that the current greedy policy is correct, right? So we don't know what is the optimal policy currently, but whenever we do Q-learning, we take a max over our current action value estimates, and so we make this hidden assumption that our current estimates are correct. At the beginning, obviously, this is going to be wrong, okay? But as the algorithm progresses, because we know that the values are converging to the right values, eventually this assumption will become correct. This is all the case in tabular. Okay? When we're doing function approximation, all bets are off. So, yes?
Can you clarify the last slide?
This one?
No, maybe with the curves.
This one?
Yeah.
Yeah, so this is showing Retrace working in the Atari games on top of Q-learning. So this is a DQ1 implementation, but which is using eligibility traces.
But how do you use traces with like a deep network?
Oh, but you can use traces with anything, right? So
When you accumulate the traces, it doesn't like have the properties when it's supposed to have, right? Since the gradients of the
So let me say a little bit more. That's a fairly involved question, but let me try to answer it without doing another lecture altogether. The eligibility trace, right? You think of the eligibility trace as being associated with every parameter in your function approximator, and it essentially keeps track of how much this parameter should be updated. And so if we are in the tabular setting, the trace is per state, and it tells us how much the state should be updated. If we have a linear approximator, we will have an eligibility for every weight. Similarly, if you have a deep network, you will have an eligibility parameter for every weight in your network. Okay? Now, it used to be the case that we always did things on trajectory, and so data would stream in. Even if you have a neural net, you would update your eligibility trace parameters, and then you would do gradient updates weighted by these eligibility trace parameters. And that is exactly the same as a usual backprop kind of update, but where you multiply the gradients that are flowing through with the eligibility, the current eligibility of every parameter. Okay? With the advent of modern deep learning, people have started using replay buffers. And so the replay buffers, the difficulty there is that you may have data sort of mashed together from multiple episodes, okay, where it's not easy anymore to compute the eligibility of a particular parameter. Now, we can do two things to remedy this. One is to say, to go back to the interpretation of eligibility traces, which is as an averaging of n-step returns, okay, and so we can use instead n-step targets and re-average them, okay. The other thing that we can do is actually to take data that is from particular trajectories where we do know what these weights are and make up our replay buffers with data like that, okay. And then when we are sampling, we do have the eligibility for doing the update that is necessary. Okay. Yeah?
What I mean is that when you accumulate the traces, you want to accumulate actually it's like a gradient every time, right? But
the trace accumulates as the gradient at that particular time step, yeah.
You want to accumulate the gradients by weighting every state that you reach, something like this. But since you also do updates while you observe another state, the parameters in your deep network also changes the.
So and we sort of in all of these implementations we sort of ignore that, right? So we're always going to use whatever our target network tells us, right? And the target network is currently a little bit stale, but we're going to use that anyway, right? So just to clarify, this particular version of this algorithm that uses a deep net has absolutely no theoretical guarantees whatsoever, right? Because we don't know, we know close to nothing about the nonlinear case. Yeah.
Do we know the behavior of the Atari games? No, right? So how do we calculate how do we do the retrace?
So in this case, we do know the behavior that was in use at the time that the data was generated, right? Because we actually played the game. And so we know the behavior at that time, and so therefore we can remember what the ratio was. Okay? Yeah?
I may have missed this, but what's the value of the importance sampling correction term for Q learning again?
So the value is either 1, right? So depending on what the behavior policy is, but it's 1 over the behavior policy or 0 over the behavior policy if I were to do simply Q-learning, right? And the caveat being that this 1 or 0 is coming actually from our current estimate of the optimal policy, which is going to be evolving over time. Okay? Yes?
So in Retrace lambda, lambda is taking the importance sampling ratio. So is this kind of justified in the sense that is this still an unbiased estimate of the return or?
So the importance sampling algorithm always gives you an unbiased estimate of the return. This particular algorithm that does the capping is no longer unbiased, right? So we essentially, one way to think about this idea, and the next idea I'm going to show you as well, is that we are going to do a trade-off between bias and variance. We are cutting, right? We're bounding the values of these ratios. That means that we're now going to be biased. The bias can be quantified based on how much we cut, right? So, you know, we can cut it at 1, and we could do something else, right? We could have a threshold there. And, of course, as that threshold becomes larger and we allow larger ratios, the bias goes away and the variance is going to explode.
Could you also explain the axis on the next slide?
On the slide? So this is basically if you play the algorithms against each other, how much would each of them win? Okay, so it's a sort of pairwise score. So in the interest of time, because I have a lot of material and very little time left, I'm going to sort of barge on a little bit here. Okay, so because I really want to show you this algorithm as well, this is a sort of another version of doing this bias variance trade-off called Retrace. It's part of this algorithm called Impala. It's a paper that came out last year from DeepMind, where the idea is to take advantage of having a massively parallel architecture where you have many actors and many learners that consume the data, and you want to have the ability for all of the learners to consume data from all of the actors. And so because the actors are all different, they're all essentially acting according to different policies. Particularly, they are updating during, perhaps during their episodes, but they're not always synchronized with each other. Okay? And so in order for this to work, you kind of have to do off-policy corrections. And so the algorithm that is used in this case is an algorithm called Retrace, which is sort of put here. So let's sort of focus on the aspects of this algorithm that are actually different, okay? So we're going to have here a product of importance sampling corrections. That's the same as before, as in Retrace, okay? So just like in Retrace, here we're going to take importance sampling ratios, we're going to cap them off according to a threshold. But furthermore, we're going to try and do this at the level of states, okay, rather than state action pairs. So that is advantageous if, for example, you have a lot of actions, right? And we're going to compute an error here, this delta TV, which is a TD error, but itself will also be weighted. Okay, now why do we need to do a weighting here? Well, this is because now we no longer have Q values, we have V values. Okay, and so the next state is going to be affected by whatever we decide to do at the current state xt. So we need to do a further importance sampling correction of pi over b to account for that here. But just like before, we're going to use some thresholding to cap this. Okay. Now, actually, rho and c play a little bit of a different role here, in the sense that rho and its thresholding is actually going to affect what you converge to. They're going to affect the fixed point to which this algorithm converges, whereas c really has the same role as importance sampling ratios have had before. Okay. So there's a couple of interesting things about this algorithm. First of all, if you're doing on-policy learning, okay, with an appropriate choice of these thresholds on C and on rho, you can actually recover exactly n-step backups. Okay? So in the on-policy case, this algorithm is capable of giving you the same efficiency that usual TD learning would. Okay? But the other interesting thing is that if we're doing tabular off-policy, you can actually explicitly quantify what you converge to. Okay, and you can sort of see the bias. all right? And so what you converge to is not the value of your target policy pi, but actually a mashup between the target policy, okay, and the behavior policy, all right? And that mashup is controlled by this rho bar, okay? So if rho bar is 0, okay, then you are on the target policy, but if it's not 0, then you can see the bias. Again, why do we do this? We do it because the variance is going to be better, right? So we have, it's another bias variance trade-off. You know, you have to accept that the values will no longer be exactly correct. Now, when you're doing control, maybe this doesn't matter so much because really what you care about is whether you're getting the right actions and not necessarily the right value function. And so if this value function still orders actions roughly right, then maybe we're okay. And so, again, the results here are quite interesting. So ignore the curves except for the reddish curves. Okay, so the bottom red curve is what happens if you just do A3C in this case, okay, without doing any kind of off-policy corrections. The higher red curves is corresponding to doing this algorithm that does the off-policy corrections. And you can see that there is a big difference here. This graph here is showing it in terms of the amount of data, okay? This other graph is showing it in terms of the amount of time spent to do the estimation. So this is wall clock time. And you can see that there is an even bigger gain in terms of the speed of these algorithms. And the other versions are just like other bells and whistles that are not relevant for the purpose of this talk. Okay. Questions or comments about this? So by the way, this is probably at the moment the best off-policy approach that we kind of have, this Impala architecture. Okay, so this is the good news. In practice, we have some algorithms that work, okay? Now I'm going to give you the bad news, okay? The bad news is with function approximation, from a theoretical point of view, everything is broken, okay? Not everything, but many things are broken, okay? Even with linear function approximation, even for just prediction and so on, we have the deadly triad. Now, Adam told me that he talked a little bit about the deadly triad, but I'm going to just recap this, this ever so slightly, okay? In off-policy learning, there are really two problems, okay? One problem is that your targets, right, that you're using to do estimation are off. And this is the problem that we've been working to correct. And this has to do with these sort of reweighting whatever returns you're getting according to the right distributions. Really, the harder problem is what happens to your input distribution, right? Because you're not seeing inputs that are in the right mix, all right? The states that you're seeing are coming from the behavior, not from the target. And having this kind of discrepancy in the input is really problematic. Now, in the tabular case, we don't care because every state has its own entry. Whenever you see a state, you're going to update its entry. That doesn't affect anybody else. If you see a state too much or too little, it just means that its entry is going to converge maybe more slowly or less slowly. But aside from that, there's no problem. Okay? However, if we start to do function approximation and we're not updating things in the right proportion, then we get divergence. And this is the very famous Baird counterexample where we're doing function approximation here. It's all linear. There's a value function that is really 0, okay, which is exactly representable with this function approximation. So it's not a problem that the approximator somehow can't represent the right function. If you put all these parameters to 0, you would be great. Unfortunately, if we do something like dynamic programming, so we sample states, we do a backup, we sample a state, we do a backup, even if you do it with the exact model, you're going to get divergence, okay? Even if you do something like TD0, you get divergence, okay? And this is an even simpler example of TD0, just to sort of get you a sense of why this is happening. So here you just have one update, you go from theta to 2 theta here. Your TD error is always going to be theta, okay? So when you're updating, of course, you're going to diverge, okay? Even though theta star is 0, and you could perfectly represent that, okay? So unless you start at 0, you're going to diverge. And really, the way to think about this is, if we sample these states in the right proportion, if we sample things on policy, these wouldn't happen. But because we don't, we're going to have a problem, okay? And so really, the instability is caused by this sort of what we call the deadly triad, okay, which is to do that we're doing function approximation with bootstrapping and with off-policy learning all at the same time. If you do just two of these things, it's fine, right? So if, for example, we're doing TD with linear function approximation, that's fine, right, for evaluating the value of a policy. But if we try to do all three of them, that's when things go wrong. Now, there's three classes of methods that can be used to solve this, and I have a copious 4 minutes to tell you about them, okay? So, I'm going to get a little bit over, and I sort of won't tell you very much about the last one. The first class of methods is what people call least squares TD. Okay, so least squares TD are essentially model-based methods. They try to estimate the transition matrix and invert it. They square the number of parameters, so that's the downside, right? So they can't handle, because of that, very, very large numbers of parameters, but they're quite stable. The second class of methods is what people call true gradient RL methods, and there's two of those. One is gradient-based TD, and the other one is proximal gradient-based TD, based on the kind of optimization that they do. And then there's emphatic TD methods. So this is work that was actually developed here at the University of Alberta that works in the linear case and essentially exploits extensions of on-policy learning algorithms. So I'm not going to tell you anything about emphatic TD. You should ask Martha White or Rupam when they give their talks about it if you want to know about that. But I will tell you a little bit about least squares TD and a little bit about gradient-based TD, just to give you a flavor of what these algorithms do. Okay. So the least squares TD algorithm, Rich doesn't like it at all, by the way, but I'm going to tell you about it anyway, because from a practical point of view, it can be very useful. And maybe Marek will tell you some things about this kind of stuff as well. I don't know. The idea here is that we could do linear least squares fits if we had the value function, okay? And so if you imagine that you want to parameterize your value function linearly, if we had the values, then we could actually do fitting, okay? We could do regression, and we could exactly solve for the parameter vector by building a matrix that is number of features by number of features, and then inverting that matrix, okay? And so this is regression. There's no divergence here, right? As long as your feature matrix is well conditioned, which we can achieve by doing various forms of regularization, this works. It's all very linear, okay? In principle, this is order n cubed, but really, typically, this is order n squared, okay? So if you have lots of features, like let's say you have a tile coder and it's got 1 million features, 1 million by 1 million, maybe you don't want to use this algorithm. But if you're in a practical setting where you have 10, 20, 40 features, right, this is a perfectly good method to use. Now, the only problem, of course, is that we don't have these targets, and so we need to put something instead of those targets. And so these different least squares algorithms make different choices about what to put there, okay? And so specifically, you have a Monte Carlo version that just puts the return. You have a temporal difference version, which puts the reward plus the value of the next state. And you can do this with an eligibility trace, in which case you put here a lambda return. And then you can just solve, okay? And now if you want to do control, you're going to do policy iteration. So you take a policy, you do the estimation, you make a greedy policy, you do the estimation again. That's called least squares policy iteration. It's an algorithm by Ron Parr back around 2003 and Mikaela Godakis. So what are the convergence properties of these algorithms? Well, on policy, okay, these do quite well. Off policy, they also do reasonably well. Notice here how the nonlinear case is all messed up. Okay, if anybody has a very ambitious thesis plan, you can think about nonlinear case. In the control case, least squares policy iteration with linear function approximation chatters around the optimal value function, right? And really, with function approximation, that's kind of what all the algorithms, the good algorithms, do. Chattering basically means that you're oscillating, okay, but not necessarily stabilizing. And you can control those oscillations, for example, by doing various tricks to sort of anneal the policies over time. Another kind of algorithm is what people call proximal gradient style algorithms. Proximal gradient algorithms, really, Mahadevan and Beaulieu did some really interesting work on that. They're based on sort of primal dual optimization. This is one particular example of such an algorithm that Ahmed Touati at Mila did in 2018. I'm not really going to have time to go through this algorithm, but I just wanted to show you what you get out of this kind of algorithm, okay? Which is, if you look at something like retrace or tree backup and you put them with function approximation, they diverge, okay? They can diverge. These are very small two-state MDPs that look a little bit like the Barrett counter example. And here is the previous algorithm that does proximal gradient, and you can see that it nicely converges. Okay? So if you're interested, you can look at the paper. What I want to do in my negative remaining time is to actually tell you about a different kind of algorithm, which is gradient-based TD. And really, the main thing that I want to show you is the geometric intuition of this algorithm, because I think that's an interesting kind of thing, and I'm not sure anybody else is going to cover that. Okay, so let's think a little bit about TD, okay? And what does TD with function approximation do? And we're going to do this in the linear case, okay? Because it's much easier to think about these things in the linear case. So in the linear case, you have a space of value functions. That's a big space, okay? But you restrict your algorithm to have to make approximations in a hyperplane, right? And this hyperplane depends on your features, and it also depends on the distribution of data, right? So how often you visit different states. And here we assume that we have a fixed policy, so this policy has some stationary distribution, there's some frequency with which you see states. That's going to tell you how this hyperplane is. And for different policies, okay, there will be different hyperplanes like this. So when you do control, right, your hyperplanes are going to shift. Okay, so now what do Bellman backups look like? What do TD-style backups look like with these kinds of hyperplanes? Well, you might have a value function here that's parameterized by theta, okay? And now we're going to do a Bellman backup, right? That means we apply either a Bellman operator or a sampled Bellman operator. So that means we take this value function v theta and we move it to a TV theta, okay? And so one way to think about this is you have some parameter vector, right? We're going to shift that parameter vector based on the rewards, and we're going to rotate it based on the transition probability distributions, okay? And so that's going to take your value function and put it somewhere out here. It's not necessarily representable any longer, exactly, but it's somewhere here. Now we're going to take that value function and project it back down, okay, on the space of feasible solutions, which is this linear space. Okay? And so if we are now doing iterations, we're going to keep repeating this. We're going to take the new value function, put it somewhere up high based on the Bellman operator, project it back down, and so on. Okay? And what we would like is to show that in this plane, these iterations are going to converge to somewhere. Okay? What happens in the nonlinear case? Okay? In the nonlinear case, of course, you don't have a plane, you actually have a manifold, right? So that's going to be nonlinear. So what can you do? Well, one way you could think of approaching the problem is to say, on this nonlinear manifold, I'm going to consider a tangent plane, right? And if I'm well behaved enough, maybe I can think and reason in terms of that tangent plane. But otherwise, it's kind of all very complicated. Okay, so now what do we want our algorithm to do? Well, first of all, let's think, what's the best possible solution here? Okay, what happens at convergence? Well, at convergence, we're going to be somewhere in this plane. We're going to take a step up, and we have to project right back down, right? Because convergence means we're no longer moving anywhere. So what we can hope to achieve is a point where v theta is equal to pi tv theta. Okay? That's a fixed point equation, and the solution we can hope to achieve is a solution of that fixed point equation. That's the best we can hope for. Okay? And so TD, its goal in life is to compute the solution to this fixed point equation. Okay, now how do we optimize this? Well, we could think of two possible things. One is to compute the error here, which is the mean squared Bellman error between v theta and tv theta. Okay? But notice that this error here actually has two components, right? So if I think of this as like a right-angled triangle, I have one component here, which is due to the fact that I've taken a step out of the plane, and really there's nothing I can do about that. Okay? That has to do with where my plane is. Okay, once I fixed my plane, I kind of, I can't really minimize this. Okay? What I can minimize is this link here that's in the plane. Okay, so the link between v theta and pi tv theta, that's what I would like to optimize. And of course, at the fixed point, this is going to be 0. So this is the mean squared projected Bellman error, okay, projected onto the plane defined by these features. And the key idea of gradient-based TD methods is actually to try and optimize this. And so I'll just sort of show you, there's a whole family of these algorithms, by the way, which again, a lot of the work was done by Hamid Mai here, Rich Sutton with some of us in Montreal. And so the idea here for these algorithms is to take this sort of geometry and turn it into an update. Okay? And so to do this, you actually have to do a bunch of algebra to try and relate the geometry to some statistics that are coming out of sampling of the data. And you end up, when you're looking at the mean squared projected Bellman error, you end up with a formula that's actually not too bad. Okay? It involves this sort of covariance part of the features, and then it involves these delta phi's. And the trick that we used is to try and use a secondary parameter vector to try and estimate some of these, to try and approximate some of these factors. Okay? And so that's sort of the crux of the algorithm. Again, we're not really going to have time to actually talk about that, but I will circulate the slides, and it's in the book. So if you want to sort of look at the math derivation, we're going to do it like that. What are the theoretical properties? So these algorithms do converge, okay, when you have a fixed policy to what would be the TD fixed point. It can be a 1-time scale result, or it can be a 2-time scale result, depending on the algorithm. And in practice, they also converge. So this is the Barrett counter example, and you can see these algorithms going down. They are nicely going down to 0 for all of them. Okay, and the inner picture is Q-learning, a Q-learning or a dynamic programming style update which diverges. And this is just another example in the game of Go. Again, looking at these algorithms, and they all are quite stable with respect to different parameter settings. The development is all done in the linear case. Again, how to do this in the nonlinear case is open. We did some work a while back, a very initial piece of work on that, but it would be interesting to figure out how to do it. Okay, so just to summarize, okay, there's lots of ways to actually do sort of reinforcement learning with off-policy convergent algorithms. There are some, okay, but not that many, at least in theory. So this is still a challenging problem. And again, there is a large variety of algorithms. And the two main things to retain out of this lecture really are the important sampling idea, right? And the fact that you can use various tricks to limit it by leveraging the problem structure, and this idea of what's the geometry of the space of value functions and how to work with that. So I'll stop there, and now I'm happy to take questions. Yep. Mm? So eligibility traces are an independent mechanism of whether you're doing Q-learning or Sarsa or TD, right? They're a credit assignment mechanism. And there's other ways of doing efficient credit assignment. Options is one of them. But eligibility traces is sort of a separate idea. Yeah. You don't need important sampling ratios, but you would do the max backup, right? And the max backup is still off balls.
All right, please,